let's get started with central limit theorem, which will define us the law of large numbers. So the key agendas today is, number one, we have to understand what is a sampling distribution. So this is a terminology that we should be very comfortable with. And what does this central limit theorem really bring to the table? What is it that it's making available for statistics? And also, the third portion, the last portion I want to cover is, when we visualize central limit theorem, what is really happening? So there is a supporting notebook also for this, but we'll look at the visualization here in the slides. First, let's get comfortable with this word sampling distribution. Let's say this is kind of my distribution of some data about, let us say in this particular case, it could be a data about number of people who survived a Titanic trip, or it could be data about salary information or the spending information. It could be anything. But then right now, what we have marked it as a population distribution, which indicates that this is the entire gamut of data that is available, or at least has been made available to us. This population distribution, as you can see, is very irregular. There is no defined mathematical function that we can put for this particular distribution. Why? Is because there are two reasons. One is, the first reason is obviously it's irregular. Second thing, it can keep changing marginally and also drastically depending on the time snapshot you're working on. So this population distribution may or may not necessarily be the right one for us to model with. So that is the first thing we should know. So what we are going to do is we are going to do something called a sampling. So what we are first going to do is we are going to take some random samples from this. Okay. And once we take the random samples, we are just basically listing out the random samples. And we are going to calculate a mean of this random sample. All right. So once we calculate the mean, I get some number. So this is kind of the mean for the random sample points that I did from this distribution. I do that again. I'm again random sampling. I'm getting another bunch of data, which is ideally different from the earlier samples. Okay. But it is not guaranteed to be different. And I'll talk about that in a minute. But some of it will be different. Some of it may not be different. Again, I calculate the mean and I get a mean value for it. Great. And I'm going to continue this process again and again and again, where I get many random sampled points and I calculate many number of means. Okay. This process of me doing is called trying to sample to build a sampling distribution. And the distribution of these means is called the sampling distribution. All right. So this is the first step to us trying to kind of bring this irregular population data into a little bit more regularized sampling distribution. Okay. And I'll show you why it is regularized, and we'll talk about that as well. But now the idea should be that we have randomly sampled, we calculated the mean, and those means, distribution of those means is called the sampling distribution. And this is one terminology that you will often get to hear, which is people will sometimes say it's normal distribution, sometimes people will say Gaussian distribution. Both are referring to the same. Then the question is, what is the distribution type of this sampling distribution? Right? We know the population distribution is irregular, but what is this distribution type? That is the key answer we are really looking for. So for that, we will inquire in a couple of different ways, just like almost like a prompt engineering with ChatGPT. We are basically revising and we are refining our question further. We're saying, is it the same as population distribution? When I sample, am I going to get the same distribution type as a population distribution? Answer is no, not always. Okay. This is a very ambiguous answer, so we're going to explore that a little bit more. But right now, just know that no, it need not be the same. Okay. The sampling distribution's shape is going to depend on three things. One, the population distribution's type. Okay. The population distribution could be a normal distribution, could be a student distribution, could be a uniform distribution, or an irregular distribution, like how we just now saw in that example. All right. So the distribution type matters here. The size of our sample also matters. The size n that we use to sample matters of how the sampling distribution shape is going to be decided. And the third one is the method of sampling, which means we have used random sampling to build a sample distribution. In our previous slide, that's what we discussed. But that need not be the only approach. People have tried various other sampling approaches like sequential sampling, stratified sampling, and these approaches will obviously build up a slightly different sampling distribution. Okay. Overall, end of the day, there will be a random element to all the samplings, whether it's purely random or if there is some sort of a slight priority with which we are picking up the neighboring data points or not, is going to define whether it is sequential, whether it is stratified, so on and so. Okay, so thus my sampling distribution shape is depending on three things: the original distribution shape, the size, and the type of sampling we approached or we applied. So let's now see what is the distribution like when my population is really normal or Gaussian distribution. Okay, so when my population distribution is Gaussian, which is very well-shaped bell curve, then my sampling distribution is also normal. So this should be no surprise to us. Meaning, yes, I sampled from a normal distribution, therefore I got a normal distribution. If I sample from a t distribution, I will still get a normal distribution. That is something we're going to learn. But right now, we have taken the most simplest scenario, which is I have sampled from a normal distribution, I end up getting a normal distribution. And this is for any sample size and any type of sampling I did. So this is an amazing realization. And in fact, it is an important learning for us, which is from a normal distribution, which is population from a population, if we sample in any size, any method, we are still going to end up with normal distribution. So use the word any size more properly. It should have some basic sample size, like 100 units, 200 units, whatever data points we took. It should not be like 1 or 2 and expect something like a normal distribution. But this is the law. Okay? This is a very important law. And what that means is, if population's mean is mu and a standard deviation of sigma, then my sampling distribution's mean is also mu. But the standard deviation is slightly size adjusted, which means it's mu by square root of n, which is nothing but the size of samples we took. So therefore, the standard deviation got a bit adjusted by the number of samples we took. So this is a size adjusted standard deviation, which is what becomes the standard deviation of the sampling distribution. And the mean continues to be the mean of my population distribution. And this is a very important realization. And in fact, it is a law. It is proven on the paper. Okay? Excellent. Now let's go to the place which really we want to explore, which is where the population distribution is not normal, is irregular. Okay? So when that happens, then my sampling distribution is still approximately normal distribution. This is one of the important areas where central limit theorem really brings the proof that sampling distribution is approximately a normal distribution. They very carefully put this word approximately, but it does really come as approximate to a very high degree normal distribution. And I will show you examples today. Okay? And this is for, there is a definition to this, which is also coming with a boundary point, which is, this is for large n values. Okay? And when we do the sampling with replacement. So here we have constrained ourselves to say, look, when your population is not normal, sampling distribution will converge to a normal distribution. If you have a large n large means at the time when they wrote it was larger than 32, but today you can consider it to be like thousands of samples, right? So that is what large is to us. And the sampling strategy we apply is sampling with replacement, okay? Which means we will take a data point from the population and we will not remove it. We will give equal chance for that data point to again get sampled in the next iteration of our random sampling. That is what it means as sampling with replacement. All right. So that's an important definition or observation that central limit theorem brings in. So what does this mean? If my population's mean is mu and standard deviation is sigma, it means my sampling distribution's mean is going to converge to mu as n increases. Okay, this is the important. So it keeps converging closer and closer to the original mu as n increases. N is the number of samples we've used. And the standard deviation is sigma by square root of n, meaning this sigma obviously is the sigma of my population distribution. If that is made available to us, then we can adjust by the sampling size we have done to get me a standard deviation, or also called the standard error for the sampling distribution. This again is a proof that is coming from central limit theorem. And we are going to see these convergent charts very soon. Let's visualize now what happens and how that convergence is really true or not. So I have a notebook obviously for this, but I'm going to show you the visualizations first. So I've taken data from a very commonly available data set called Boston housing data set. Okay, it has a lot of house prices and stuff, but we have taken in the tax column because it had some interesting shape, which is very irregular. And what is important here to see is, yes, I have my data in X and my frequencies are plotted in my Y, and I have my mu, which is the overall mu of the population that has been given to me, about 408.27, and my sigma 168.537. In this case, calculating a sigma for this distribution may or may not even be a stable thing. But what we did with this process is just to confirm that it is not going to infinity. That's all. Which means it is a stable distribution. That's all we have proven by this. We are not going to be able to use this number in our crunching so comfortably at this stage. So we'll do sampling. We'll sample with n equal to 20 with replacement. Okay? Then we get a distribution like this. So what does this mean? I have possibly run 1,000 iterations as I sampled, but every time I sampled, I took 20 data points from here for the 1,000 iterations, and I kept calculating the mean for those sampled 20, and I plotted them out here. And what do I get? I get some choppy distribution, still not regular. And look at the mean, where it is. 410.338. Standard error is off. That is because it has to be obviously weight adjusted, and what we get here is more usable standard error than, like I said, for the population distribution. So in this case, the mu is a bit off just by 2 points. It is still not 1,500 or something like that, like 800. If we would have sampled, see here, we could have very well got some large number also, but that is not the case. Magically, with the 1,000 iterations of me doing the sampling and doing the mean, I got a mu closer to this, but not too close to it. Okay, so we're going to see by pushing the n more and more will give us something a little bit more closer to the genuine population. Okay, so we have taken definitely a slice from here, randomly 20 points. We have essentially taken that slice, summarized it through the mean, and then brought it over here into the sampling distribution. And we are saying that distribution is having a mu that is converging to the population. Again, we take the same data. Now we have sampled n equal to 120. So we have increased it. It's with replacement. Remember that, because without replacement will not give us this result. All right. So we have taken it with replacement, and obviously we have run about 1,000 iterations. So that is important. The iteration, if it is too low, right, you're not going to get this much data filled up. Remember that. So whenever people show you a sampling distribution, there are two things you need to ask them. Tell me the number of iterations you ran, and also the sample rate. So here the sample rate is 120, which means I'm taking a slice of 120 points each time, taking the mean and plotting them here. But I'm doing that for how many times? How many iterations? 1,000 iterations. So that I have a healthy build up here. But what is again important to see is, because I increased it, there is also a possibility that I was getting something out here. A lot more samples could have come from here, and that is very likely possible, correct? Because each of this point is equally likely to come when I do the random sampling. All right. So there is also a statistical rule that 67% of those that slice that we take is unique. Okay. Statistically, 33% could be the duplicates from the previous time when we sampled. So that is statistically possible when we use a sampling with replacement. All right. So 67% is unique, is guaranteed to be unique statistically. It's proven again from the random sampling with replacement. So therefore, what if a lot more came from here? That is still fine, because what we have essentially done is that summarization via the mean has really got them compressed into a good representation, getting it closer and closer to a genuine mean, which is itself an average across the entire set of data points. Okay. So thus, I'm getting a little bit more better distribution shape. Still not normal, but a little bit more closer. And let's see this. The mean has already started converging. 408.59. Earlier, it was 410. Now it's 408. Let's see. Let's increase this more and see how it plays out. Now we take it up more. N equal to 1020. Now what happens is the mean is dipping down 407.86, a bit away, but it's much closer to obviously around the same population distribution, and your standard error gets a lot more crisper. Why? Because now I have more sample data points, a better representation of the slice is coming in as it fills up each data point here. That is the important thing. So same 1,000 iterations happened earlier also, now also, but then here it is more crisper and smoother because better representation has come from here to this point, meaning the means we computed out of the 110 are more crisper and accumulating more and more closer with each other. Okay, and then let's try a couple more times. 2,120 samples, 1,000 iterations, and now we see that distribution is getting very, very seriously close to a normal distribution, because this blue line I've drawn here is the representation of a normal distribution. So there is no doubt that this is getting closer and closer as it fills them up. Okay, we don't even see too much kurtosis. We don't even see too much of fat tails here. So those are properties of normal distribution people usually look for. Okay, as data scientist, you will definitely be given a lot of data, but then also be asked to do analysis on the data. So at that point in time, whichever tools you use, the tools will give you the plots, no problem. But then how do we analyze that plot is the important skill that we should do, which is questioning the points we have to question, look at certain areas within a distribution for us to assess whether it's going the right direction or not. Okay. And finally, we also try once more, almost close to 4,000 data points each time. And we get absolutely close to a normal distribution. And also, we see here, see this mean, 408,139, 408,237. It's getting closer and closer and closer as we increase this for the 1,000 iterations. And this standard error now is more seriously useful for us, because all it says is, look, my mean is around about 408.13, and one standard deviation is about 10 points away, okay, compared to the mean. However, here, it is just way too off. It says the mean is around 408.23, and one standard deviation is 168 points away, which is just too big. So if you take a ratio of 168 by 408, you will get a much larger ratio, which tells us that this standard deviation is just too off. It is too big for us to operate reliably. Whereas this one, much, much, much closer. Okay? So that's the key takeaway that we should have right now of how using sampling with distribution, sampling with replacement on an irregular population distribution is giving us a sample the distribution, which is the sampling distribution, much closer and approximating from a mean perspective to the population, and also is operable from our mathematical perspective because it is converged or converging to a Gaussian distribution. So the benefit of this is we will no more need to do splines and curves and fittings. Rather, we can just depend on the Gaussian distributions, probability maths, to just compute what is the probability that a particular point may arise. That is a question we usually ask, right? What is the probability that particular point may arise? We may ask that question in multiple ways, either as a standard question like that, or we may ask the question, what is the rareness that this particular point may occur? Let us say this is distribution of Boston data housing set and we have taken taxes. Can we ask the question, what is the probability that people pay less than 350 for taxes? It is right in the tail here. So probability is very low. Most of the people are paying somewhere down here, 400 to 420. Okay? So such questions about the tail and the probability can also be answered very accurately. And based on that, again, we can build a classifier, whether it is a standard machine learning classifier or to validate a neural classifier. Okay?